Okay. Good morning, everybody. Let's see. So, it turns out I'm actually ahead of where we're supposed to be right now, which is a good thing. It means that for the rest of this week we can relax the pace a little bit and kind of dig into these concepts in a little bit more depth. I posted the homework. The homework is going to be due not this Friday, but the coming Friday. Okay, so no homework due this Friday. The homework that's due next Friday is like 35 questions long, so not quite double the length of your usual assignment. So that's what's going on with the homework. Your exams are all graded and entered into Blackboard. Please check the comments that I put on there. Unfortunately, I can't put as many comments on your digital exam as I can on like your physical paper just because of how long it takes to get through it with the Apple Pencil on the iPad. It's a miserable experience. So if you want a little bit more feedback on why you miss points, or if you're confused on why you miss points and you want to know, just send me an email. We can set up a time to talk outside of office hours or during office hours if that works as well. Any questions about logistical aspects of the class? Homework, exams, grade? Okay, if not, then let's try these warm-up problems on your own for a while, and then we will talk about them together. All right, how we feeling? Anybody get stumped by these warm-up problems? It's okay, no shame. We thought it was hard. Everyone. Okay. All right, well, that just means we should talk about Riemann sums a little bit more. Well, since we all thought it was hard, why don't we do them together? I won't torture you guys by asking for volunteers. Okay, so n equals 4. What is that telling me in terms of this problem? What is that information? N equals 4. Yasmin?
How many sections of the graph you're going to have? So
Yeah.
4 lines, 0, 0, 4.
Yep, we're going to have 4 rectangles. So I guess, let's see, how many lines are we going to need? We'll have to use 5 lines, I guess, if you include the end lines, I think. Whatever, let's draw and find out. So we go from 0 to 4. So let's see here. 1, 2, 3, 4. And e to the x, that's an exponential function. Exponential functions grow faster and faster and faster. The reason I put this point here is because this is the point 0, and then if I plug in e to the 0, that would be that point there, and e to the 0 I would get 1, so that'd be 0, 1. All right, so that's why I draw that point there. That's going back, way, way back to our exponential stuff. So I just want to draw a picture of this thing. That's all I'm doing. And it looks something like, well, that doesn't go through the dot, does it? It looks something like this. Okay, so we're doing the integral from 0 to 4. So let's draw in red the region that I want to get the area of. It's going to go from here to here. And I'm supposed to use 4 rectangles. Okay. So if I'm using 4 rectangles, how wide should each rectangle be? What should the width of each rectangle be if I use 4 rectangles to partition my domain here, which is 4 units wide? Yeah, it should be 1 unit wide each, right? Okay, so that's something that I want to really quickly mention, is sometimes you'll see this notation delta x. Okay, now remember, this delta thing kind of means change in x. Okay. In the context of a Riemann sum problem, delta x refers to the width of each rectangle. Okay. The way we find delta x for a Riemann sum problem, say we were doing the integral from a to b of f of x dx and using n rectangles, the way we find delta x is going to be equal to b minus a over n. So what is this top thing? The thing on the top, b minus a, that's the width of our interval. We divide it by the number of rectangles, and that's how we get the width of each rectangle. Okay, it's not always going to be nicely equal to 1, like it is in this problem. Okay, so when on your homework you see things that ask you about what delta x is, that's what they're talking about. It's the width of each rectangle. And this is how you find it, b minus a over n. In our case, b is 4, a is 0, so we do 4 minus 0 over n. We're supposed to use 4 rectangles. 4 minus 4, or 4 minus 0 over 4 is 1. Okay, so that's how we get the width of each rectangle. Okay, now what's left to decide is how to pick the height of each rectangle. How should I pick the height of each rectangle for this problem? Yasmin?
Based on if you're using a left or a right Riemann sum?
Yes. So we should pick the height of the rectangle based on whether we're doing a left-hand sum or a right-hand sum. For our problem, they tell us to do a right-hand sum. So my rectangles are going to be, why don't we, let's pick a good color for this. We'll do right-hand sum, we'll do green. Okay, so for each interval, which I am told should be 1 unit wide, these are where my rectangles are going to lie. The height of each rectangle should be chosen by taking the height of the function on the right side of each subinterval. So here I go drawing. I'm just going to pick that height there on the right side of this first interval, and that's going to be the height of my first rectangle. And so on and so forth. I'm just going to choose the height of the next rectangle to be the height of the function on the right side of the interval. And I'm going to keep doing that. Okay, and I'm going to use these rectangles to approximate the area that's entrapped by this red, well, the area that's under the curve. Should I draw it? Sure, I'll draw it. I'll draw it with gray. I'm trying to estimate this area here. So I say, well, something that's pretty close is going to be these green rectangles. Okay, so how do I find the area of each rectangle? So let's start by trying to answer this question. We want to say integral from 0 to 4 of e to the x dx is approximately equal to, and now we should write something down, which should be the area, the combined area of all of these rectangles. Let's start with the first rectangle, shaded in green. How do I find its area? I find the area of a rectangle by doing base times height. What's the base? Kevin?
1.
Yeah, just 1 unit wide. And how tall is it? Yeah?
You just said it's e to the x.
You're very close. But e to the x is a function. I'm looking for a number.
E to the 1.
Yeah, e to the 1. We should take 1, which is the x value on the right side of this interval. We plug it into e, and that's how we know how tall our first rectangle is. Because this point right here, we decided that the height of the rectangle would be the height of the function on the right side of the interval. So if I want to know the height of the rectangle, I just take the x value, which corresponds to the right side of the interval, and I plug it into the function e to the x. So since the right side of this interval it ends at x equals 1, I take x equals 1 and I plug it into e to the x, and I get e to the 1. So the height of this guy is e to the 1. Okay, all of these guys are going to be width 1. What's this height here going to be? Yeah, Mia? Yeah, e squared. And then the third one is going to be e cubed. And then the fourth one is going to be e to the 4th power. Okay, so what I should do now is add up the areas of each of these rectangles. The first rectangle has base 1 and height e to the 1, and then I should add the second rectangle has base 1 and height e squared, and I should add the third one has base 1 times height e cubed, and then I finally add base 1 times e to the 4th power. As usual, I did not leave myself enough space to do the second problem. Okay, so that's all just equal to, let's see, 1 plus 2, that's 3, plus 3 is 6, plus 4 is 10, e to the 10th, right? E to the 1 plus e squared plus e cubed plus e to the 4th is e to the 10. Something wrong with my simplification here? Yeah.
Can't you not do that because it's a variable? Well, not a variable.
Yeah, I definitely can't do that. This is a power here, okay? We can't take, if we take x squared plus x cubed, we definitely don't get x to the 5th. Okay, we can't add those things like that. If we took x squared times x cubed, we would get x to the 5th. Okay, I'm just testing you guys here. This is definitely not true. We can't do that. We should just leave it as, if you want to write it a little bit more clean, you could write e to the 1st plus e squared plus e cubed plus e to the 4th. These are not like terms. We cannot combine like terms. We could try to say, I mean, we could take 1 power of e out. We can make it e times 1 plus e squared plus e to the 4th cubed, if you want. Doesn't really matter. Okay, so that's how we do this. We just find the height of these rectangles and the width of the rectangles, and then we add up all of their areas. So one thing that I want to point out is, or maybe ask you guys, do you think that this estimate is an overestimate or an underestimate of the actual area? Yeah? Yeah, it's an overestimate, right? Because all of my rectangles are actually, I have a lot of overestimation here. These green shaded regions here are all surplus area that will be included in my estimate, but wouldn't be included in the actual area under the curve. So we call this an overestimate, okay? If I had done a left Riemann sum, I'll draw it in with orange. If I had done a left Riemann sum for this function, I would have gotten an underestimate, okay? Left Riemann sums will not always be underestimates. Sometimes the left-hand sum will be the overestimate and the right-hand sum will be the underestimate. Sometimes they'll both be an overestimate. That's possible. Or both be an underestimate. But we got to draw the picture to see. Okay? All right. So on your homework, I think there are a couple problems that ask you to compute Riemann sums, and then they ask you whether you think your sum is an overestimate or an underestimate. So that's what they're talking about on those problems. Questions about problem 1? Warm-up problem 1? Okay, I'm going to come back to warm-up problem B a little bit later, but I want to make sure we can get through some things that I want to talk about today. And let's see how I want to talk about it. Okay, here's how I want to talk about it. So far we've said that integral from a to b of f of x dx is the area under the curve. But what if f of x is negative? So let's have a picture. Why don't I draw that a little bit higher? So here's our coordinate axis, and I'm going to draw on a function here, f of x. I'm going to call this point A and this point B. My question is, how do I do integral from a to b of f of x dx now? Any guesses? Should we do this? Should we try to just take, you know, all of this area down here, area under the curve? What's that going to get us if we do that? If we just take this rectangle here, which goes on and on forever, and we take its area, what are we going to get? Yeah, we'd get infinity, okay? So this is not a good way of understanding the integral from a to b of this function. What could we do instead? Yasmin?
The area above the curve.
Yeah, area above the curve. So more explicitly, we could kind of expand our understanding of the integral from area under the curve to being more like area between the curve and the x-axis. Okay, so here's what we're going to do. You're really close, Yasmin. We're going to take this area here and say this has area equals to 25. We define integral from a to b of f of x dx to be equal to negative 25. Okay, so the area between the function and the x-axis is 25, but since our function is beneath the x-axis, we're going to call that integral negative. Okay, so this region has positive area. However, the integral in this case is actually going to be negative. Okay? So let's have another example. Let's try this one. Let's have f of x, which looks like that. It's f of x. And let's call this region, this point 10, and we'll call this point obviously 0. And now let's try to compute the integral from 0 to 10 of f of x dx. Okay, let's also call this point here 5. Hang on, have I taught something like this before? Okay, I guess I better back up a little bit. I might cut this and put it down a little bit and say one thing really fast that we're gonna need to know. Here are some rules for definite integrals. First of all, the integral from a to b of f of x dx, let's call it the integral from a to c, is equal to the integral from a to b of f of x dx plus the integral from b to c of f of x dx, where the corresponding picture for this is if I have a here and b here, then this area, which is shaded in green, this should have been c on the right hand side, sorry, c, and then b is somewhere in between. Then this shaded region in green is equal to the shaded area in red plus the blue shaded area. Hopefully you believe that. Okay, that's what this rule is saying. So we can split up an integral into pieces. Okay, we can find the area of like the first 10 feet and then the second 20 feet, and that'll give us the area of the first 20 feet. Okay. So that's one rule. And let's just keep that one for now. So I'm going to use that rule on this integral here. Let's -5, and let's call this 5. If I want to find the integral from 0 to 10 of f of x dx, well, I know I can split that up into the integral from 0 to 5 of f of x dx plus the integral from 5 to 10 of f of x dx. And now let's work on computing each of these. For the first one, it just looks like one that we've already done. We want to find this area shaded in red here. That's what we're trying to do for this first one. So if we try to do that, well, we can see that the width of this is just 5. The height of it is 5. So if we take the area of that triangle, we take 1/2 times 25, and we get 25 over 2. Now we'll do a plus sign, and now let's compute the area, or rather the integral from 5 to 10 of f of x dx, using the rule that we just used. So I know that f of x in this region is beneath the x-axis. So what I should do to compute the integral from 5 to 10 of this function, I should take the area that's between this function and the x-axis and take the negative of that area. That's what's going to be the integral from 5 to 10 of this function. So this, again, just has, this is just a triangle with base 5 and height 5. So we get 25 over 2, but we make it negative since f of x lies beneath the x-axis. So in this problem, we took one integral, split it up into two integrals, and we found that each integral had the same value but opposite sign. If we add them together, what are we going to get? Yeah, 0 is what I'm hearing. Okay, so in this case, the area above the curve canceled out the area beneath the curve. Okay? So, we can expand our understanding of the integral from a to b of f of x dx as being equal to area enclosed above the x-axis minus the area enclosed beneath the x-axis. Okay. So this is our little bit expanded understanding of this integration process. Okay, so let's have some practice with problem number 2, okay? So, they tell us the area of each of these regions, and we're supposed to find the value of each of these integrals, okay? So this should help us get some practice here. So the first one, integral from 0 to 2. So, we're just going to take the area from 0 to 2, and that's it. So it looks like on our graph that's corresponding to 2.5. So I'm just going to write 2.5. Okay, so that's that first integral. Okay, second one, we want to do the integral from 2 to 3. Okay, from 2 to 3. So I'm considering this region in between these two green lines. If I want to do the integral of the function, for this region the function lies beneath the x-axis. So I'm going to take any area which is enclosed between the function and the x-axis and negate it. So what should I get for integral from 2 to 3 of f of x dx? Kevin?
Negative 0.75.
Yeah, just negative 0.75. Okay, so now let's try this third one here. C is going to be a little bit trickier. Now we're going not from 2 to 3, but from 0 to 3. So, let's apply this new understanding here. We should take the area enclosed above the axis, x-axis, and we should subtract from that the area enclosed beneath the x-axis. So, I can write this as two integrals using my special little rule. I could write this as the integral from 0 to 2 of f of x dx plus the integral from 2 to 3 of f of x dx. And I already know what each of these two integrals are. This was a, and the second one was b. So this is just 2.5 plus negative 0.75. Or, in other words, 2.5 minus 0.75. Right? Adding a negative is the same as subtracting. Okay. What do we think for D? What should we do for D? We want to take the integral from 0 to 4. Yeah, Andrew?
3.75.
3.75. So let's see, 4.5 minus 0.75. Yes, I think 3.75 is going to be right. And the way we did that was we took 2.5 plus 2 That's the area above the x-axis. And we subtracted from that the area beneath the x-axis, which was 0.75. So that's 4.5 minus 0.75 equals 3.75. Very good. Thank you, Andrew. Okay, so this is kind of how we do this stuff, okay? We just take the area above the curve and subtract from that the area beneath the curve. Okay. Maybe we'll come back to that. There's one more thing I want to cover before we get done for today, and that's area between two functions. Okay. Say I have two functions. First function, f of x. Second function, g of x. And we're interested in knowing what is this area which is trapped between A and B, which is trapped between these two curves. So, we've learned a lot about how we can find area using integrals. Okay, finding area using integrals. We want to think about how we can find out what the area of this region is. So let me step back and ask a leading question here. Just going to take us back to geometry. Say I have a square, which is 4 by 4. And inside the square, I cut out a circle from it. And the circle has radius 1. How do I find the area of the shaded region? Yeah.
The area of the square and the area of the circle and subtract this circle from the square.
Absolutely. Very good. So Mia says take the area of square and subtract area of circle. So in our case, that would give us 16 minus pi times 1 squared is just pi. Okay, so 16 minus pi, that's how we would get that. So how can we use this kind of technique to find out the area between these two curves using integration? Yasmin?
You do the area under the curve f of x minus the area of the curve of g of x.
Exactly. We can find this, the area of this region, by taking area under f of x and subtract the area under g of x. How can we write that mathematically? What is the area under f of x from A to B? Yes, Yasmin?
Integral from a to b of f of x d of x minus integral a to b of g of x.
Very good. And I can actually use one of my rules for integration to combine this into a single integral. we said that the integral of a sum or a difference is equal to the sum or the difference of those integrals. So we sometimes write this instead as the integral from a to b of f of x minus g of x dx. Okay, so let me just give you a quick illustration for what's going on here. What we're doing is we're taking this blue area here, and we say, okay, let's subtract from that the red area here. So if we get rid of the bottom piece, then we'll be left with the stuff that's in between. Okay, and we write that integral from a to b of f of x minus g of x dx. Any questions so far? Okay. So let's try this thing here. Let's try, not that one. Let's try this one. Problem 5. We want to express the area between the curves y equals x squared and 8 minus x squared as an integral. So let's have a picture of what's going on here. Y equals x squared, that's just a parabola. Whoa, that got wonky. Okay, there's x squared. And then we have 8 minus x squared, which looks like a parabola which opens down. It starts here at 8, and it opens down like this. Okay, so they say the area between these two curves, we want to express that. So that's this area here, which is kind of trapped between two parabolas. That's the area that we want to express as an integral. So we know it should be the integral from a to b of our top function minus our bottom function. So the way I could write that would be 8 minus x squared. That's the top function. Subtract the bottom function, x squared, dx. But there's still a lingering question here. The lingering question is, what are a and b? Supposed to express this as an integral. We need to know what the limits of integration should be. How could I find out what the limits of integration are? Where should I start and stop recording area? If I'm moving from left to right on the x-axis, where should I start and stop, Yasmin? Say again?
Where the two functions intersect.
Yeah, where the two functions intersect. So this point and this point, that's where we should start and stop. Okay, so what we should really do is just like integrate from here starting at A and here starting at B, or ending at B, and just do all of this stuff in between. And count all of that area, and then we'll be done. Is there a way I can find out what A and B are? Kevin?
Did you set them equal to each other?
Yeah, I can set the two equations equal to each other. If I do that and solve for x, then I'll know the x values that cause these two graphs to intersect. So I'll take x squared and I'll set it equal to 8 minus x squared. I'll add x squared to both sides. I get 2x squared equals 8. I'll divide by 2. I get x squared equals 4. And I take the square root. And I get plus or minus 2. So What do we think a and b should be? We should do the integral from what to what? Yeah, -2 to 2. So let's include that in our integral. We should do the integral from -2 to 2 of 8 minus x squared dx. Okay, I think that's all we have time for today. Next time, we're going to finally put all of this stuff and learn a good way to actually compute integrals in general. If you have questions or you want to see more examples, stay after class and we can chat for a bit. Yep. Ryan, you got some questions?
Can we just do the warm-up problem that we didn't do?
Oh yeah, sure. We can do the warm-up problem. Okay, so we were supposed to find, let me clear a little space for us here. We're supposed to find this area under the curve here using 4 rectangles and a right-hand sum. Okay, so the first step with all of these is always just to draw a picture. What does x squared minus 4 look like?
Parabola with a minimum of 4.
Yep. So here's 4, and the parabola just looks like this, maybe. Okay. Next thing to do is to put on our limits of integration onto the graph. -2 and 6. So we go from -2 here. We got 1, 2, 3, 4, 5, 6. Let me extend this a little bit further. Okay. So we're supposed to use 4 rectangles. What should delta x be for this problem?
6 minus -2 over 4.
So I get 8 over 4 equals 2. So each rectangle should be 2 units wide. Okay, so let's draw on the bases of each rectangle. First rectangle is going to go from here to here. Second one will go from here to here, and then from there to there, and from there to there. So these are going to be our rectangles. Now, how should I choose the height of each rectangle?
Plug it into the function.
Plug what into the function?
The x value.
Which x value?
On the right-hand side.
Yeah, on the right-hand side of each rectangle. So what's the right-hand side point for the first rectangle?
0.
Yeah, I'm going to take 0, and I'm going to plug that into our function to get the height of this first rectangle, and I'll extend it to the left. Okay, call it a right Riemann sum because we decide the rectangle should be the height of the function on the right side of the interval. All right, how about the next one? I should take x equals 2, find the height at that point, push it over to the left. It's our second rectangle. Then I should take x equals 4. Oops, I don't know why that happens. X equals 4. Move it over to the left like that. And then lastly, I should take x equals 6 and move it over to the left like that. Okay, so I'm pretty much there. The only thing I need to do is compute the area of each of these rectangles. I know that each one is 2 units wide. And let's start by figuring out what is the height of the first one. Well, I should take 0 and plug it into the equation x squared plus 4. What do I get?
4.
Just 4. Okay, and how about this one here? What should I do to get that height?
2 squared plus 4.
Okay, and I get
8.
8. And the next one?
4 squared plus 4.
Mm-hmm.
20.
And how about this last one?
6 squared plus 4, so it'd be 40.
Yep. All right, so I'm nearly there. Now it's time to write down the integral from -2 to 6 of x squared plus 4 dx is approximately equal to, what goes in the blank?
All of them added up.
Okay, so what do I get?
68 plus 4, 72.
Okay, hang on, let's see here. Not quite.
Oh, no, yeah.
Not quite.
68 plus 4. No, not mine. 68 plus 4.
You're nearly there.
40, 50, 60.
So far you've added up the height of each rectangle. What are we supposed to be adding up?
By 2.
Yeah, we have to take 2 times each of those numbers, right?
Yeah.
So we should get 2 times 4 plus 2 times 8 plus 2 times 20 plus 2 times 40. So you're going to get whatever you said, 72 times 2.
144.
Yeah. Okay, so that's how we do that. We just take the area of each of those rectangles and add them up, but we got to be a little bit careful since this time the width wasn't 1. So we got fortunate on the last one, and what I tried to write out, I tried to be very careful about the way I wrote it out. I wrote it out like 1 times e to the 1 plus 1 times e to the 2 plus 1 times e cubed plus 1 times e to the 4th. This was to try to really point out the fact that what are all of these things? They're areas. It's not just me adding up the height of the function. Okay, so that's how we do these Riemann sums. And if I wanted to do a left Riemann sum, the only thing that would change would be the height of the functions. So I would take this point instead, and then I would take this point, and then I would take this point, and then I would take this point, and I would make all of these rectangles to be my new basis for my integration, and I would get that the integral from -2 to 6 of x squared plus 4 is going to be approximately equal to, and I would take, let's see, -2 squared plus 4. This height would be -2 squared plus 4 would be 8, and then 0, this one's going to be 4, and then this one here is going to be 8 again, and then this one here would be, what is that, 4, that one's going to be 20. So on this one I would get 2 times 8 plus 2 times 4 plus 2 times 8 plus 2 times 20, and I would get, what, 16 plus 8 plus 16 plus 40 equals, let's see, 32 plus 8 plus 40 is equal to 80. Is that right? 16 plus 16 is 32, plus 8 is 40. Yeah. So yeah, I guess that last term there really made that a super overestimate, didn't it? Yeah, and it makes sense, by the way, if you look at this, because look at how much taller the green rectangles are than the orange ones. We have one orange rectangle, which is an overestimate, but all the rest of them are underestimates. Yeah. Whereas if you look at the green ones, all these three are overestimates, and only this one is an underestimate. Okay. So we got pretty wildly different answers here. The reason is this is just an approximation. Okay, we're not finding the actual area under the curve. We're finding something which is kind of close. Any further questions on this Riemann sum stuff?
No, I can actually understand it pretty well.
Okay. Do you have any questions about any of the other integration things that we covered today?
Not really. We could finish the problem, I guess, but we didn't finish it if you want.
Which one was that?
Like the very bottom one. Like the area between. We didn't like find the area between.
Oh yeah, that's because the problem just asked us to express the area between the curves as an integral, which we've done. Okay. That's this integral here. If you did it and found that area, that would be the area between those two curves. And what is it really? It's really just it's really just the area underneath the upside down parabola, and I just subtract from it the area underneath this right side up parabola, right? So if I take all of the area that's trapped between this thing here and the x-axis, and I subtract that little piece at the bottom, then I'm gonna get whatever's in between. So that's what we did, and we're gonna get to actually evaluating these integrals on Friday using something called the fundamental theorem of calculus. We're going to use antiderivatives to do it, and it's going to make things much, much easier than doing this Riemann stuff.
Okay. Well, for derivatives, didn't we do that too? Like we found the hard way first, and then
yeah, it's really similar to that. We got to do it. We got to do this awful approximation stuff first, and then we're going to learn why calculus is awesome. Because right now we're doing the non-calculus way, and it sucks. So we're going to learn the calculus way and see why that's so much better. Okay.
Thank you.
Yep, no problem.